Hi everyone, this is PGD AI machine learning with Python, and this is being the session 6.1, which will be covering advanced machine learning using linear regression, and our expert Jaimit Vasawa, who has been conducting this study circle for almost 6 months now. It's a privilege to have him provide us the learning what he has done and help all the participants to be able to use. The details of the link are already put out on the chat window. You can refer to that. Meanwhile, I'll ask Jaymeet Vasawa to take over from here. Thanks, Jaymeet. Let's have a great talk. Yep, go ahead.
Yeah, so thanks for the wonderful introduction. And so welcome everyone for the machine learning with Python. And this is the sixth session, 6.1 on advanced machine learning. So let's get started with the session. So for this session's objectives will be understanding some of the foundations of the machine learning algorithms, difference between the supervised and the unsupervised learning algorithms, understand and develop the gradient descent optimization algorithm used for understanding or getting the optimal values of the bias and weights. Then applying the machine learning algorithms available in scikit-learn to regression and classification problems. And then discuss the problems of underfitting and overfitting and how to control them using regularization. How to apply ensemble techniques for random forest, which are bagging and boosting. Know what is a hyperparameter and how to search for optimal hyperparameters. Then learn feature selection using machine learning models. So we'll start with some of the basics first. So for AI, you can see the Venn diagram. This is something that we have used again and again in order to get the relationship between AI, ML, and DL right, and get the further topics staged together with this. So you can see that Venn diagram, which shows the DL being subset of ML, ML being subset of AI. So under the ML categories, we have supervised, unsupervised, and reinforced learning. These are some of the most common categories that are talked about for the machine learning and categories. So for supervised, there are classification and regression. Classification for binary or multi-class, whether one class is whether the picture contains a cat in it or not, it becomes binary. Multi-class means how many animals can a model recognize, becomes a classification. Then regression for predicting the continuous values. Then comes the unsupervised learning, where the model has to predict or learn the patterns within the data, and we do not have the output or the outcome variable, unlike supervised learning. Clustering, when data points plotted in a 2D space, and the similar data points are plotted into the same vicinity and are grouped together in a way, shows the similarity between them, is called clustering. Association is nothing but creating an association with different items. A person buying breakfast, if if the person buys milk, some of the recommendations or associations that can be made with milk for breakfast can be bread or eggs. Then comes dimension reduction. It's a technique for preserving the originality of the dataset while having few features, or only having the most impactful features. Then comes reinforced learning, which is nothing but based on penalty and reward, and the model learns based on that penalty and reward mechanism. Or you can also say that it can also learn from trial and error methods. So two of the topics that we'll discuss before starting the advanced topics are statistic-based learning and objective-based learning. Statistic-based learning, we collect the data, analyze, interpret, present, and organize the data. It provides a robust set of tools for understanding patterns and making inferences and predictions based on the data that we have, or the data uh, which we are working on or with. When we are dealing with large data sets, statistics helps us understand and summarize the data, allowing us to make sense of complex phenomena, normality of residuals, significance of the regression parameters, and so on. Then comes the objective-based learning, where it allows the computer to learn from and make decisions or predictions based on the data. The ultimate goal of the machine learning is to create models that can adapt and improve over time with the change in the data, as well as change in data with time as well. So in the case of a random forest using classification trees, the most important objective is the accuracy or performance of the model. So two of the topics that we have already discussed are supervised and the unsupervised learning. Supervised learning, we have the output variable, which we have to predict with the help of the input variables or the feature variables or the values that we already have. And we predict the outcome variable for the new records and the values of the input variables. Linear regression and logistic regressions are examples of the supervised learning algorithms. For unsupervised learning, the datasets will have only input variable values, but not the output variable values, or we do not have the output variable. The algorithm learns the structure in the input. Clustering and factor analysis are examples of unsupervised learning. So how does a machine learn? Specifically speaking, how does a machine learn in supervised learning? So as we talked about the outcome variable, and we already have the values of the outcome variable. So what would be the one way to decide how much is our machine or the model that we are training is efficient? We basically try to compare the values that are the actual values and the predicted values. So which is basically what a cost function or the loss function does in supervised learning. It is an error in between predicted outcome and the desired outcome. For a function where n is total number of records, h of xi is the predicted output and yi is the desired output. The expression of the sum of squared error, the expression you can see on the screen, which is L equals to 1 by n for n records, the summation of all starting from I equals to 1 to n, h of xi minus yi, the whole square. This is used for minimizing the loss function. We use optimization algorithms like gradient descent or Bayesian optimization, etc. In this topic, we will be discussing the gradient descent. So in gradient descent algorithm, you can see the first equation, which is a simple linear equation, y equals to beta 0, the intercept, plus beta 1 xi, beta 1 being the coefficient of the xi observation, plus the error, which is epsilon I. The predicted value of yi, which is denoted by yi hat, is given by the yi hat equals to beta 0 hat plus beta 1 hat xi, where beta 0 and beta 1 are the equations or the estimated values of the intercept and the coefficients. And the error, which was mentioned in the simple linear equation, is given by the difference of yi minus yi hat, or the actual value minus the predicted or the estimated value. And when we substitute the value of y hat with the beta 0 hat values, we get the term y minus beta 0 hat minus beta 1 hat xi. Now, for the mean square error of the total n records is given by 1 by n summation of I equals to 1 to n, and yi minus beta 0 hat minus beta 1 hat xi, the whole square. So the gradient descent finds the optimal values of the beta 0 and beta 1 that minimizes the loss function using the following steps. So before we start, I will just summarize a bit of it. So gradient, we are going in the opposite direction and finding the global minima of the convex curve we have, which will give us the least loss values for our equation, and which makes our model the most efficient, the least loss making our model the most efficient one. So let's discuss the steps. The first step, randomly guess the initial values of beta 0, which is the intercept, and beta 1, which is the feature value or the feature weight. Calculating the estimated value of the outcome variable yi for initialized values of bias and the weights. Calculate the mean square error function, MSE, and then adjust the beta 0 and the beta 1 values by calculating the gradients of the error function. So the values of beta 0 hat. So for the terms that are the mathematical terms, on the left hand side, those are beta 0 hat and not just beta 0. So those are beta 0 hat equals to beta 0 minus alpha, which is the learning rate, into partial derivative of the error with respect to beta 0. Same for beta 1 hat equals to beta 1 minus learning rate into partial derivative of error with respect to beta 1. And for the comment on the graph, you can see the graph, the gradient is going down, and the minimum value is what we are aiming for. So the value of learning rate, which is alpha, and also a hyperparameter, is chosen based on the magnitude of update needed to be applied to the bias and the weights at each iteration. So the partial derivatives that were mentioned before, we get the values of them for the partial derivatives of error with respect to beta 0 and beta 1 are given by -2 by n with summation of I equals to 1 to n for all the records, and y minus yi hat, which is basically the difference of the actual minus the predicted value. The same for partial derivative with respect to beta 1 is minus 2 by n, summation of I equals to 1 till n, into uh, for yi minus yi hat into xi. Now repeating these steps of 1 to 4 for several iterations until error stops reducing further or the change in cost is infinitesimally small. The values of beta 0 and beta 1 at the minimum cost points are best estimates of the model parameters. So these steps that we started with randomly initializing the value, calculating the estimate values of y, and then calculating the mean square error and adjusting the values of beta 0 and beta 1. These are repeated until we get the error to as small as possible. So developing a gradient descent algorithm for a linear regression now. So for understanding the gradient descent algorithm, we'll use a linear regression model on a data set of advertisement where the advertisement on TV, radio, and newspapers are used, and the revenue that are generated due to those advertisements on different time periods are taken. The data set is taken from the book Introduction of Statistical Learning by James and others. And the description of the dataset you can see, which contains the TV, radio, newspaper ads, and the sales revenue generated due to them. So we already got our X and Y values. The X values are TV, radio, and newspaper, and the prediction values are the Y value, which is the sales. So developing the gradient descent algorithm for a linear regression model. So we'll start with importing the needed packages of pandas and numpy, then reading the data set. We'll just suppress the warnings with filter warnings, ignore, and then just printing few of the records on the data set. And you can see the screenshot of the records. Now we have already known the X and the Y values. The X are the values on which we will be predicting the value of Y. So before we start the X and working with X and Y variables that we have already defined, some of the comments regarding the process that are being done for this. So a common technique known as feature scaling, specifically a standardization. So standardization transforms the variables in a data set so that they have a mean of 0 and a standard deviation of 1. This process is beneficial for many machine learning algorithms, particularly those that are sensitive to the scale of the input features. The optimization algorithms, in our case, the gradient descent, the goal is to minimize the cost function. So we move in the opposite direction of the gradient, which is downhill, to reach the optimal parameter values that minimize the error. Remember this graph, and we are trying to get to the minimum error. So it is important to convert all the variables into one scale. So this can be done by subtracting the mean from each value of the variable and dividing by the corresponding standard deviation of the variable. So that is what we will be doing for the Y and the X values. For X, we will be using just the anonymous function or the lambda function and do the subtracting the mean. from each value and then dividing by the standard deviation. The same is been done for the y values as well. Now, implementing the gradient descents, we have four methods. Method to randomly initialize the bias and weights, method to calculate the predicted value of y, that is y given the bias and the weights, and method to calculate the cost function from predicted and the actual values of y. Then the fourth method to calculate the gradients and adjust the bias and weights. So let's get started with method one. So random initialization of the bias and weights. So first we will define a function called initialize, which will take a parameter dim. We'll keep a seed value or the random seed value of 42. We'll use to initialize the bias, we'll use a random function of the Python, because we don't need any we don't need the biases value to follow any kind of distribution. It's a real just a second. So so the biases value does not need to be need to follow any kind of distribution, and it's a random value. So we can use the Python's random function for that. But for weights, it does have to follow a normal distribution. So we'll use the numpy's random function for it. Then using the initialize method for the TV, radio, and newspaper, which are the or advertisement mediums. So we'll use the initialize value of 3 and get the values of the bias and the weights. And you can see when we use the initialized value for the bias and the weights, and the values that we get for bias is 0.63, and for the weights of TV, radio, and newspaper in that specific order, we get for TV 0.37, for radio 0.95, and newspaper 0.73. The method 2 is predict y values from the bias and weights. So we'll use the matrix multiplication of weights with input variable values. So the matmul method of the NumPy library is used for the matrix multiplication that we'll be needing for it. So each row of x can be multiplied with the weight column to produce the predicted outcome variable. So we'll define the function prediction y, which will contain the bias, weight, and the x values, and return them with the bias and the matrix multiplication of weights with the x values, or the observations of observations, or the variables with the coefficients. So calculate the predicted values of the initialized bias and weights, and the predicted values, which in the mathematical equation we said as y hat, or the estimated values were denoted by y hat. So we'll have a variable y hat and save the predicted values of y over here. And when we print the 10 values of the y hat, and the values you can see starting from 0.23, 1.7, all the way to minus 0.76. So this matrix multiplication operation allows us to efficiently calculate the predictions for all input samples in one go, which is the essence of using the matrix multiplication in regression model in general. Now calculate the cost function MSE. So calculating the okay. So this is the method 3, where we calculate the cost function. So computing the mean squared error (MSE), calculating the difference between the estimated y and the actual value, calculating the square of the above residuals, the difference basically, and sum over all the records and dividing it with the number of observations. So we'll be following the same thing that we just stated verbally in the code. So we'll be using we'll be defining a get cost function, which will take the values of actual values of y and the predicted values of y, which was the step 1 over here. So in the comments, you can see the step 1 and 2 and 3 and how they are taken, which will return the values of 2 and 3 by conducting the calculations, which were to calculate the square of the above residuals, the difference basically, and calculate the sum of it, and then dividing with the number of observations. So this is what the get cost function does. And then using the get cost function on the y and the y hat values with the bias and the weights, the output is a 1.53. So the fourth method is update the bias and the weights. Based on the gradient of the cost function, the bias and the weights will be updated in a method update beta using the following gradient. So this is nothing but just referring to the already discussed beta 0 hat and the beta 1 hat uh, expressions that we have seen in the beginning of the session, where beta 0 being the intercept, beta 1 being the coefficient, alpha being the learning rate. So we'll be translating these mathematical equations into code. So the nomenclatures in general, what we'll be using are x and y for the input and output variables, y hat for the predicted values of with the current bias and weights that we have, and B0 and W0 for storing the current bias and weights values, and learning rate in order to see the effect of which are the suitable learning rate for us for the optimum results. So update beta, you can see the parameters x, y hat, bias 0, weight 0, and learning rate. Basically, what we have done is we have translated the mathematical expression over here into this, and then basically returning the values in form of a beta 1, in form of bias 1 and the weight 1. So so first, as we have been saying the learning rate and stuff again and again. So this time we'll be using the learning rate. We'll start it with the learning rate of 0.01. First, we initialize it with the current weight that we have, then using it on the update beta, and using the learning rate as well at the end, which is 0.01, and then printing the results of it. So you can see the results of the bias and the weight. The bias after the initialization was 0.63, and the weights for TV, radio, and newspaper in that order is a 0.37, 0.95, and 0.73. These were the older values. After the update, the bias is 0.62, the weights are 0.38, 0.93, and 0.71 for TV, radio, and newspaper. So we have been talking about learning rate again and again, but just a small summary for how the learning rate works, especially for the people who are listening about it or learning about it for the first time. So step size, it's nothing but a larger step size consists of larger steps, or the larger learning rate consisting of larger steps, while the smaller learning rate consists of smaller steps. Then there is something called convergence, where convergence is basically a term used for models when after reaching a convergence, a model will not uh, improve further on it. So that is what we call convergence. So a higher learning rate may lead to faster convergence, but may also reach the minimum, but may also overshoot the value of reaching the minimum value of error. So basically, we cannot hasten the process of convergence, but lower by keeping a higher learning rate. But conversely to it, the lower learning rate may result in slower convergence, but may be more stable and less likely to overshoot the value of the minimum error. Then tuning the hyperparameter, it's it's an experimentation thing. If we have to go through different iterations and check the performance of the model on the validation dataset and decide the tuning of the hyperparameters. Then grid search or random search. Common approaches to finding a suitable learning rate include grid search, or trying a predefined set of learning rates, or random search, sampling learning rates randomly from a predefined range. Additionally, adaptive learning rate techniques such as ADAGRAD or adaptive gradation, then RMS prop and ADAM dynamically adjust the learning rate during the training based on the gradient's history. And last, regularization. The learning rate can also interact with other hyperparameters, such as regularization parameters, and act the model's generalization performance. As it's essential to consider the learning rate in the context of other hyperparameters during the model tuning. So this was just a short summary on the learning rate and how to get started to work with it. Now, finding the optimal bias and the weights. So to update the bias and the weights, we need to be done iteratively. So basically, we are going to pass through several iterations of the data set in order to get the optimal values for the bias and the weights that we are trying to search. So there are two approaches to stop the iterations, because it's a time-consuming process and it can take several iterations. The two approaches that we can opt for are run a fixed number of iterations and use the bias and weights as optimal values at the end of these iterations, then run the iterations until the change in cost is small, that is less than a predefined value. So as we went for a learning rate of 0.01, we can also go for a more slower learning rate of 0.001. So we'll define a method to get the values of the optimal bias and weights and get started to how to find it. We'll use or we'll define a method called run gradient descent, which will accept the parameters of learning rate and the number of iterations. Now this run gradient descent will invoke the initialize method, prediction of y values method, that we have used, then get cost method, and the update beta method. These all the methods that we have used in the past will be invoked by the this method. So variable GD iterations DF, which is just the data frame to keep track of the 10 iterations that we have decided over here to keep track of them. And the default value of the learning rate is a 0.01 over here. And the number of iterations that will be used for this will be 100. So I kind of summarized the run gradient descent before. So the x, y, then the value of the learning rate and the number of iterations 100. So initializing the values of weight, then getting the GD iterations data frame to store the value of all every 10 iterations, then running the iterations using a for loop, which will take the value of estimated or the predicted value of y, then use the this cost function, basically getting the current value of the cost function, storing the values of previous bias and the weights, then update and calculate the new values of the bias and the weights, and storing the cost of mean square error for every 10 iterations. And finally, printing the estimate of the bias and weight. So when we use this run gradient descent function that we just defined on the current values of bias and weights for the alpha value or the learning rate value of 0.001, and for the number of iterations, instead of 100, 200, this is the value we get for the bias and weight, which is for bias it's 0.42, and for the weight is 0.48, 0.75, and 0.46. And we print the values of it, the GD iterations data frame that we used to keep track of every 10 iterations. You can see the first 10 iterations starting with 0 through 9. Now plotting the points of the cost function against the number of iterations that we have. So we'll be using the matplotlib and the cbon library, and just plot the iterations and the cost on y and x. And the final estimates of the bias and weights that we got over here are again printed over here for the reference to keep in mind. So this is the plot that we get for the cost function against the number of iterations that we get, and you can see that our cost keeps on declining further. So we'll be checking it further too, that whether it declines further or not. And also the weights are standardized values, as we have used standardized values of y and x. This means that for one standard deviation change in TV spend, the sales revenue changes by 1.55 standard deviations, and so on. So as from the graph, you can see the value of cost keeps on declining with the number of iterations, we'll be using the values of uh, with the learning rate of 0.01 and 0.001, and this is what the code of first and second line says. And also the number of iterations are 2000 this time. So when we plot the different learning rates of 0.01 and 0.001, you can see the graph that we get. So the learning rate of 0.01 is faster than learning rate of 0.001, but can miss the minimum value of the cost function, and we have to search for the optimal value of the learning parameter. So these were some of the basics that we have used NumPy for. Now we'll be discussing a linear regression model using the scikit-learn library for machine learning. So we have covered some of the basics using the NumPy library. Now I'll be using the scikit-learn, and the reasons to use a scikit-learn are it contains a comprehensive set of algorithms for following kind of problems, which are regression, classification, then clustering. And along with that, the methods for data pre-processing and the feature selection as well. So the steps to be followed for building a machine learning model, validating a machine learning model, and measuring its accuracy are: identify the features and outcome variable in the dataset, split the dataset into training and test sets, build the model using the training set, predict the outcome variable using a test set, compare the predicted and the actual values of the outcome variable in the test set, and measure the accuracy using the measures using a mean absolute percentage error or root mean squared error. So this can be a kind of a reference for working with most of the machine learning models, except if you go for specific, the last 0.5 is for linear regression, but this kind of sets up a reference for the machine learning models when you start to work with, especially if you are new and beginning to try some of the machine learning models. So first, whenever we start with the machine learning model, we start with data. So we first split the data set that we are working with into the test and train data sets. So we'll do it for the X and Y values of the train and test data set, then train and test data sets for X and Y values, both of them, which is present in the scikit-learn's model selection. So just in case, if you also want to check the uh, the observations under the training set of X and the training test set of X, you can check it using the length function of Python. So building a linear regression model with a trained data set. So we'll be using the scikit-learn's linear module to build the linear regression model and implement the gradient descent algorithm on the model that we will be building. So first, we'll be initializing the model using the linear regression model on the linreg uh, variable. Then trying fitting the model with the train data sets of x and y values. And for and running that, we get the output of linear regression. The copy x equals to true, the fit intercept true, and the number of jobs that it will take while working the data set is equals to 1, because we are not parallelly working with anything else. So number of jobs is 1. Normalize is the normalized values of the x, which is false over here. Copy x is true because it creates a copy of the values of x. Then for getting the values of the bias and the weights for our linear regression model, so we can uh, use intercept and then the underscore values for the coefficient as well as the intercept and get the values of them. For intercept, we are getting the value of 2.70, and for the coefficients 0.044, 0.199, and 0.006 in the order of TV, radio, and newspaper. To associate the coefficient values with a variable, basically we are trying to have them together, the values of the variables as well as the actual values of the coefficients. So we'll be using the set function and presenting them as a list. So so for these values and for the intercept value of 2.70 that we got here, remember the equation of yi that we also discussed before. This is the equation that we get. So when we substitute the corresponding values into the equation, this is what we get, or this is how it looks like for the corresponding variables for when they are substituted in the expression. So of course it's a mathematical equation, so they are basically indicating the unit change with the variable values. So for every unit change, 0.044 is the unit change for TV, 0.199 is the unit change for radio, and 0.006 is the unit change for the newspaper. So we need to standardize the values for the model now. So making the prediction on the test set, we have been using the training data set. Now we'll be using the test set. So we'll be using the scikit-learn's predict method on the model we built and predict the output of on our test set. So it's the same thing, but using it on the test set of the spread that we used for splitting the data set, and then comparing the value of the actual and the predicted values and storing it in the data frame called test prediction df or test spread df. So test spread df is a pd.data frame and then getting the giving the values of the corresponding values to it. And if we or when we just print out 10 samples of the data frame that we just created, this is the screenshot to it. Now measuring the accuracy using the root mean square error and the R squared error. So starting with the R squared value, calculating on the training data set. So remember the R squared value is calculated on the training data set. So importing the needed matrix, which is a matrix, then use the matrix on R2 score for the Y train, the regressions predicted values on the X train, and then predicting the values of R squared, we get the value of 0.90, which means it is able to understand the 90% of the variance in the Y. Now the other the measure of accuracy is RSME or RMSE, which is a root mean squared error. So we'll be using metrics again. That is the reason we imported it. So metrics dot mean squared error takes the value of actual and the predicted values and returns its mean squared error. So using the needed giving passing the needed parameters to it, and routing the value of MSE and rounding the value, and then printing the value of it, we get the value of 1.95. So it shows that the model prediction having that standard deviation of 1.95. So to improve the model, we need to understand the components of the error term and the how to deal with those components. So a bias and variance trade-off. So what we'll be understanding here or discussing about here in this topic is we'll be trying to understand the error of the models and what it means. So two of the components important for it are bias and variance. So knowing them helps model accuracies and avoid over and underfitting of the models. The high bias can lead to building underfitting models, whereas high variance can lead to overfitting models. So we'll use the we'll use a different data set called curve.csv over here in order to understand the bias and the variance trade-off. So first reading the data set, then just printing few of the records on the data set, and you can see the screenshot of it. Now plotting the values of the data set. So of course it's not a linear relationship, and there is a polynomial relationship between the values of x and y. So let's learn about them. So polyfit is a function from a NumPy library which takes x and y values and degree of x features to be used to fit a model. So simplifying it further, the degree 1 means only value of x is used to predict y, whereas degree 2 means x square are used to predict the value of y. It's a common technique when you work with polyfit models. So we'll be defining a fit poly method, which is a generic method which takes the degree as a parameter and builds the model with all the required polynomial terms. So the first defining the method fit poly, which takes the parameter of degree, Then getting the values of for the curve x, then draw the regression line after fitting the model and plot the values of x and y. Now, this is the same equation that we have been working with. So remember, we are using the degree of 1 to start with. And when we plot the values of it using the degree of 1, okay, the mathematical equation that is which shows beta 1 is actually beta 0. So please just keep that in mind. So the when we plot the values of values for the x and y and draw a regression line, it's not fitting the model, and you can see the statement regarding the graph plot. The model has underfitting or bias issue, and it is not able to learn the data to its form or the way data is. So we'll be using the degree 2 now for the fit poly method that we have defined, and using it for the equation. And you can see the mathematical equation over here for the reference. And when we plot the graph, you can see that the now the data points are fitting, or the model is fitting the data points very well. So the regression line is fitting nicely compared to the previous model that we have for the graph. So now we'll be checking whether this was the best model, or we can still improve further. So we'll be using, as we started with a range or a degree 1, we'll use it on the range of 1 to 10 now, and see what are the results we get. And doing it again for the fit poly method and plotting the graph. This is the graph that we get for doing it in the range of 1 to 10. So an underfitting model has a large error because of high bias, and an overfitting model has a large error because of high variance. Something that we also mentioned before. An optimal model will be somewhere between an underfitting and an overfitting model, and we will have low bias and low variance. So this can be observed by comparing the root mean squared error in training and the test data sets. So we'll be building the model for the degree of 1 to 15, and then storing the values of them in the data frame. So the terms we will be using are degree, showing the degree of the model, RSMA train, RSMA error for the training data set, RSMA test for the testing data set. So you splitting the data set again. We are splitting the data set into 60-40 using the random state or a feed of 100, and assigning the data frame the columns and its name, getting the value of the root mean square error for the y and the y fit, and then looping through using the for loop of 1, 1 to 15. And storing those values in the RMSE data frame that we created. So when we print the RSMEDF, this is what the values look like for the degree, for the train, and the test data split. So when we plot the graph for the train and test split, or the test data, train and test data sets, this is the graph that we get. So observations from the graph are the test set error are high for degree 1 to 15. Then test set error reduces at first and then rises continuously. You can see the above line is increasing. At first, or at the initialization step, it was declining, but then it kept on increasing. And the training error sets are continuously decreasing. So the degree can also be associated with complexity. It can be observed that the complexity, which is number of polynomial terms in the model, increases. The model starts to fit to train and test data as well. But beyond a specific level of complexity, which is for 5 over here for us, the training error continues to reduce, but the test error starts to increase again. So this is the point where the model starts to overfit the training set and stops generalizing. So the optimal model complexity is 5 for us, which has a low bias and the low variance. You can see the result of it over here. Till 5, it was all good for test and the training both. Last is a k-fold cross-validation, which is used for verifying the whether the model is overfitting or not. If the model generalizes well and doesn't overfit, it will work well with any data samples and will not be sensitive to change. So we are talking about the a model which is working well around our estimates and is not showing any sign of overfitting or underfitting. So it won't be sensitive to change in the data. So k-fold cross-validation can do this by building and validating the multiple models by resampling multiple training and validation sets from the original data set. So as it's a validation approach to verify the model's overfitting, it will be using the various multiple training data and validation data sets from the original data set as well. So the steps that are used in k-fold cross-validation: split the training set and data set into k subsets of equal size. Each subset will be called a fold. Let the folds be labeled from f1 through fk, whatever is the value of k that we will decide. Generally, the k's value are 5 or 10. For I equals to 1 to k, the fold fi is used as a validation set, and the remaining k minus 1 folds as a training set. So basically what we are doing is having a data set, dividing it into 10 equal forms. If we have taken the value of k equals to 10, then using k minus 1, which means 9 data sets for training and 1 data set for validation set, and train the model using the training set and calculate the accuracy of the model in FI. So the final accuracy obtained by averaging accuracies across all k models on test data reflects the model performance in the real world, while variance of these accuracies indicate model robustness. As you will see this, see the this screenshot, you will get what the k fold cross validation does. This is for 5 iterations for the value of 5 or a k's value of 5. So we are splitting the data set into 5 parts, where we are using 5 minus 1, 4 splits for training and 1 split for testing. So this is what we meant over here. So for 5 iterations and for 5 folds, this is what it would look like. So to summarize the today's session, we'll start by looking at the Jupyter Notebooks codes, and we'll start summarizing the today's session. So we started with the advertising data set for a TV, radio, newspaper, and seeing and the revenue in different time periods. So we imported the needed packages and read the data set and printed few of the records, first 5 records. Then we set the variables, which were X and Y, X for the TV, radio, and newspaper, and the sales to be predicted on Y. Then standardizing the values of Y and X. X is 0 basically means that we are working with columns. Then implementing the gradient descent algorithm, where we discuss the 4 methods. Method 1, randomly initializing the values of bias and weights. We define the initialize method having a parameter of dim. And when we run the initialize method, for three parameters, which were TV, radio, newspaper, these are the values for bias, and these were the values for weights. In the order of in the weights are in order of TV, radio, and newspaper. Then the method 2 was predict the Y values from the bias and the weights. And we used the matrix multiplication over here. And when we initialize the values of it and got the top 10 values, this is what we got. The method 3 was cost function of MSE, mean squared error. We defined a get cost to get the residual of it, and using it on a Y hat, we got the value of 1.5. Then method 4 was to update the bias and weights. We defined a function method beta, which took x, y hat, bias 0, weight 0 values, and the learning rate. So using the learning rate of 0.01, we initialize the value of with the current bias and weight, and updated the value of bias and weight after. And this is what the initialized or the previous bias and weight values, and these are the values of after the updation. finding the optimal bias and the weights. We defined the run gradient descent, which invoked a lot of methods like initialize, get cost, update beta, all of them that we did used before under this method as well. We also made a data frame to keep track of every 10 iterations, as well as every 10 iterations uh, every 10 iterations cost, which is mean squared error to be stored. And then using the run gradient descent on the GD iteration DF with the alpha value of 0.001 instead of 0.01, 0.001, and the number of iterations of 200. These were the values of bias and weight that we got for it. If we print the values of the gradient descent iterations after first 10 or 11 to be specific, this is output that we get. Then we plot the cost function against the number of iterations that we are doing. So basically, we are trying to get the loss function based on the number of iterations that we're getting and what is the relation and what are we getting. So when we plot, this is the graph that we are getting for the number of the cost and the number of iteration. So as the you can see the with the increasing iteration, it is decreasing. So we are trying to get whether it decreases further or not. So we are getting the values of different values of bias and weights again using the different alpha values as well as the number of iterations. Here we are using the alpha 0.01, then we are using the alpha values of 0.001 and the number of iterations of 2000, and this is the bias and weight values that we are getting. TV, radio, and newspaper, and that are for the weights. And when we plot the values of different alpha values or the learning rate values, this is the plot that we get. And you can see that 0.01 learns faster and 0.001 has a kind of a slower learning rate, but 0.01 also has the risk of overshooting the minimum value and not finding it. So these were some of the basics that we covered for using NumPy, and now we'll be using the scikit-learn for the machine learning. We followed these steps. So first was to split the data sets into train and test. Using the seed value of 42 in order to reproduce the result. Then just in case if we want to check the values within the train and the test of X split, 140 and the 60 are the respective observations within the X train and the X test dataset. Using the scikit-learn's linear model and importing the linear regression, we used a linrig as our saving variable. Then fitting the model using the X and Y's train split. Then to get the values of the linear regression model, which is linreg over here, and get the values of the intercept and the coefficient values of that model. This is what we get. This is the value of the intercept, and this is the values of the coefficient of it. These are the values of the coefficient of them. We are just zipping the values of TV, radio, newspaper with the values of the coefficients. So these are the values of TV, for the radio, and the newspaper. Now, I'm making the prediction on test data, which is the step 3. So using making y prediction or y pred on our linear regression model on the test set of X, and storing the result in the data frame, and you test pred df, and printing the 10 samples on the test pred df that we got. This is the output that we get. Then measuring the accuracy of the model that we have created. We remember we used R square and root mean squared. So using the scikit-learn's matrix for being able to use the R square as well as the mean squared error. Then first we use it for R square. This is the value that we get, which is 0.90 or 90%. And for RSME or root mean squared error, we get 1.95. The 1.95 can still be improved. For the standard deviation, so learning the bias and variance trade-off using the curve.csv dataset. So first reading the dataset and printing top 5 values or top 5 records of the dataset, plotting the values of X and Y. This is the plot that we get, and you can see it's not a linear relationship, it has a polynomial relationship. So we'll be using the polyfit method of NumPy, and we'll be defining our own fit poly method and using the polyfit within it, which takes X value, Y value, and the degree. Now, as we have defined the fit poly method using it, so these are the same code, by the way. So using the fit poly method and plotting the graph, this is the graph that we get, and it still does not fit the data points. So the model is not still learning the data. So this is the result for degree 1, fit poly 1. Now for degree 2, we are getting a better fit of the model, but we'll still try to see whether the model that we are using can improve or not, or is this the best model that we have. So instead of using so this time we'll be using the degree value of 10, and you can see the fit that we are getting, and we are getting the improvement. This is the previous model with degree 2. This is the model with degree value 10. So we decide to build a model using degree 1 to 15 and store them in the data frame. These are the terms that we used for degree, root mean squared error on the trained dataset, and root mean squared error on the test dataset. So we define a function get RSME, which is nothing but the root mean squared error. Then iterating through it, iterating through the degrees of 1 to 15, and storing the results in the RSMEDF or RMSE data frame. And when printing the data frame, these are the values that we get. Now, plotting these values on the training and the test data, this is the plot that we get. And you can see that the test data set, it declines initially, and then after 5, it keeps on rising. Whereas on the training data set, it declines and keeps on declining after 5. So some of the observations that we can take from the plot that we saw, which were test error are high for degree 1 to 15, test set errors reduce at first and rises continuously, the green one, and the test set error, training set errors are continuously decreasing. Then we discussed about the k-fold cross validation, where we split the data set and we use the k-1 splits for training and the leftover one for the testing. And we go through iterations for it. So this is it for the session 6.1. The next session would be 6.2, which will be on advanced regression model. These are the common references that are used. Not much of the outside references are used for this session. So this is it for 6.1, and thanks a lot for listening. Thank you.
Thank you, Jamit, for the excellent presentation. Nishu, you have anything you want to ask? Anybody? Any questions? I think we'll end the session, and if you have any questions, you can send the questions to info@uotf.in, and we'll have that answered. Plus, you can also go to the YouTube and connect to the link which was given in the chat window and send your comments. And so let's look forward to seeing again on Monday. Jamit will thank you for the presentation, and I will end the recording here, and then we can, if you want anything, you can also